Hi, I'm Max. This is the first day of the Collisions and Explosions camp, and today we'll be making a spoon catapult and talking about how it works and how the same concepts are applied in real life.
So for the spoon catapult, we need a piece of tape, 12 to 15 rubber bands, a bottle cap, and 11 popsicle sticks. We start by taking 2 popsicle sticks and rubber banding them together near the tip. And then we repeat that with 2 more popsicle sticks, and we try and rubber band them at about the same place on both pairs. Then we get another 2 and rubber band them, except we want to make the angle very square. We want to give it a 90-degree angle and really get it right up to the tip of each popsicle stick. And you can move them around after you finish rubber banding them if you want. And now we add another one. It doesn't really matter which side, pick your favorite, and rubber band that as well. And we add the final stick, and this time we have to rubber band both ends. So we start with this end, and now we do the final end, which is a bit tricky because you can't really loop it around, so you do whatever works. And now you get those first 2 pieces, and you have to kind of slot them in the middle, and then you use rubber bands and wrap around the edge to hold them in place. This will make the structure for our catapult. Now, if any time I'm going too fast, you can always just slow down the video or rewind it. And now we secure the other side to the frame of the popsicle sticks. It's okay if it's a bit wobbly. We'll add support later on. And now we repeat with the other side of the frame, with the other pair of popsicle sticks. And we get the final popsicle stick secured to the frame. Now we get another popsicle stick and we put it on top. And then we just add a rubber band and wrap it between the connection of all 3 of them. And we repeat with the other side of the popsicle stick. If it's uneven, you can always just push them across and adjust them. And now we add the popsicle stick that will be the pivot point for the arm. This one's kind of a bit tricky because you have to loop it across the side a few times, and then you can just rotate the popsicle stick around to the front, like I do here. And then you have to secure the other side of the popsicle stick to the A-frame of the catapult. And voila, we finished the frame. Now we get the final stick, and we use some tape. I would suggest using more than I do in this video. We use some tape to attach the bottle cap to the stick. You can also use hot glue, although be careful if you use hot glue, and you can use glue, anything else really. You just gotta get it stuck there. And then you get a larger rubber band, and you attach the bottom of that to the back two corners. And you're done.
Catapults are pretty cool because even though they're able to fling these little objects really far, they're actually really simple. And I'll show you why. So if you look at it from the side, you have this triangle structure right here, and then you have the arm, which mounts right here, and then it like starts going flat, okay? And then you have the basket right here. And all this arm does is it travels up like that. And now if you've learned about simple machines, you'll recognize that this right here is just a lever. Except these can be really big. Several hundred years ago, people would use these to fling huge stones at big castle walls to knock them down. So even though this is a really simple machine and a really simple device, this can get a lot done. And this just shows you that even simple machines can do a lot. And this entire system works through a pretty simple and predictable way, which I think is really cool. So, if you do have this catapult here, and then you shoot a rock, okay? So the catapult is the lever arm is going to stop when it's going up like this, okay? So the rock is going to travel in that. If gravity were to not exist, the rock would travel in this dashed line forever. But we have gravity, so actually what happens is gravity is always pulling down, because that's what gravity does. It always pulls down. So this rock will actually start to go down from that line, and then eventually it'll hit the ground. And this shape is actually really cool. If you were to extend this shape beyond where this arm goes and beyond the ground, so you just keep drawing it here and here, then you'll get something that looks like this. And this is called a parabola. It's actually a fairly complex mathematical line, and you'll definitely learn about it later in school. But what this means is that the height of this line at any point, so over here or over here or over here, the distance from the ground, which say is here, so that would be here, that distance, or here, or here. This is always changing by a different amount, okay? And this is a bit complex. If it were changing by the same amount, you would actually just get a line like that. And you can see, so this is here, so you have that distance, and then 2 times over, right here, you actually have double the distance. So that means this is changing by this same amount. But this isn't true. You can see it goes up, and then at right here, it turns around and goes down. And this is because some really complex physics. But I think this is really cool, because every single rock, or every single projectile that will ever be shot by a catapult will actually follow this path. Although different portions of it, depending on the angle that it ends at, because this angle right here can be different. Let's say you make it right here, you won't get that much power, and it'll kind of shoot it up, and it'll go in a much sharper path. So if this was squeezed, and it would just go, and if it stopped right here, it would kind of go up and then down again. But then another one is if it stopped much later. So if it stopped like here, right before it goes vertical, then it would be very, 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 very shallow. Okay, so it wouldn't go up that much, and then it'd go down and hit the ground. And that's all just from stretching and squeezing this type of curve, which I think is pretty cool. And this same concept obviously was applied several hundred years ago to make machines that would knock down castle walls. But now, levers are used for tons and tons and tons of things. Sometimes really, really, really huge, but sometimes very small. One simple example would be in a car. There's a lever that changes the gears, and the gears control how fast the engine moves the wheels. And then if you drive a manual car, which is like a special kind where you can control them yourself, you are really just using a lever to shift over the gears. And that's like another use case of levers. They're also used in like machinery, where you use levers to control the machine, like how high it moves various parts of it. Like if you have a bulldozer, you can use a lever to control how high it has the shovel thing. And so even though it's a simple machine, it's going to be everywhere, and you can see it everywhere you look. Even toys like seesaws and stuff like that. Okay, this is all I have for you today. But if you have any questions or any comments, you can go down to the Zoom link in the description of the video. And at 1 o'clock, I'll be hosting a Zoom session, and so you can just like pop in, say hi, and then we can talk about whatever you have. Or if you just like have random things to ask, explosions or collisions related, I'm open. See ya.